Hi everyone. Today I will present a paper entitled PrivateSQL, a differentially private SQL query engine. And this paper is accepted to VLDB 2019. Here is the outline of this talk. I will first briefly introduce some backgrounds and motivation, and then I will introduce the design of the private SQL. Nowadays, the data accumulates over the years, and we are now in a big data era. And with the big data, we can use it in many application scenarios. For example, the data can be used for statistical analysis and for training machine learning models and for intrusive advertising. But at the same time, we also want our data to be kept private. Consider a motivating example of the U.S. Census, and it is a once a decade operation where every household in the United States will be asked to answer a series of questions, and the results will influence the policy making and the planning for the next decade, such as the congressional apportionment and the redistricting and the summary files releasing. And here we only focus on the summary files releasing, since one can make statistical queries through SQL queries. For example, one can issue accounting queries to find how many people with age ranging from 18 to 25. But according to the law, nobody, including the officers of the Bureau, is allowed to make any sensitive or personally identifiable information public. To address the privacy issue, the differential privacy has become a golden standard. And still, considering the census, for example, well, the Census Bureau can be viewed as a trusted curator. And after collecting personal data, the Census Bureau will add some form of noise to the aggregated data before releasing it. And the noisy database, on one hand, can protect privacy of every individual, and on the other hand, it allows an untrusted analyst to make statistical SQL queries. So what is differential privacy? A random formally it is defined as below. A randomized mechanism M satisfies epsilon differential privacy if for any neighboring databases X and Y and any output O of the mechanism M, the inequality holds. And informally, it ensures that the presence or absence of a single record, and this is the neighboring database has minimum influence on the outcome. And differential privacy has been adopted by many well-established companies for private analysis, such for example, Apple studies the usage of emojis and health data with differential privacy, and Google analyzed the setting of the Chrome with differential privacy. At the same time, differential privacy has many desired properties, and a differentially private algorithm supports post-processing, which means that running any algorithm on the output of a differentially private mechanism M does not incur extra privacy loss. And the sequential execution of two differential private mechanism is also differentially private. And this is called the composition theorem. For example, and let M1 and M2 be epsilon1 differentially private and epsilon2 differentially private. Then their combination is epsilon1 plus epsilon2 differentially private. In addition, there is an important notion called the sensitivity, and it is defined as the maximum change of a query or function and neighboring databases. For example, the sensitivity of counting queries is 1, since the adding or removing a single row will change the count by at most 1. And the scale of the added noise depends on the sensitivity of the query or the function. And existing differentially private algorithms only consider a database that has only one relation. That is the database differ in only one row in the relation table. But in real world, the database systems are always very complex, which have multiple relation tables. And here is a simple example of a database with 2 relation tables, and person and household. Besides, there are 2 types of key constraints, the primary key and the foreign key. And the primary key for a relation table is defined as an attribute or a set of attributes that can uniquely identify its rows. And the foreign key is used to link 2 relations, and it also acts as a primary key for one relation. And in the given example, the house ID HID is the primary key in the household relation table, but the house ID HID is the foreign key in the person table. Then the real question is how to define neighboring multi-relational databases. Before giving its definition, we first summarize the goals of the PrivateSQL. First of all, it needs to support a workload of complex SQL queries on a multi-relational database. Second, it can use a fixed privacy budget for all the queries. And lastly, it allows the data owner to define privacy requirements. For supporting a workload of queries, one can apply a differentially private DP algorithm for each query. And this is indeed the key idea of a VLDB18 work. But it is easy to see that this method would incur unbounded privacy loss according to the composition theorem, or the data owner stops answering queries if a privacy budget is reached. Moreover, the query answers are also inconsistent, which means that for the same query, the output may be different, since a differentially private algorithm is randomized. And one can also generate a synthetic database, which is differentially private for multiple queries. Although this approach addresses the above 2 shortcomings, but it does not support generating the synthetic multi-relational databases. On the other hand, performing join operations on each synthetic single relational database incurs large errors, and in practice, the larger error results in worse utility. Before presenting the detailed construction, I first briefly introduce its high-level idea. And for supporting a workload of queries, The data owner will generate and release multiple differentially private synopses. And with this synopsis, we can use a fixed privacy budget among them and obtain consistent query answers. And the synopses are generated using views instead of the base relation tables themselves. And essentially, a view can be interpreted as a SQL algebra expression which can capture join operations of the base relations. And this solves the problem that the queries involving joins cannot be answered accurately using the simple synopsis of the base relations. And each view is used to answer only a part of queries, since we cannot accurately answer an arbitrary number of queries under strong privacy guarantees. Now, let me introduce the model of the private SQL. The data owner takes as input a database with multiple relations R and a workload of queries Q and a fixed privacy budget epsilon. And the private SQL has two main operational phases: the synopsis generation and the query answering phases. And the generated private synopsis can be used to answer the query workload without additional privacy nodes. And this phase is the focus of this paper, which has 5 modules: the view selector, the view rewrite, the sensitivity calculator, and the budget allocator, and the private synopsis generator. And the query answering phase only provides an SQL interface to the analyst and computes answers to the queries based on the private synopses. For the view selector module, it generates multiple views based on the query workload Q and the base relations R. And each query in the workload is linear answerable using one view. And linearly answerable means that a query can be answered without additional complex operations like joins. And each view can answer a part of the workload where the queries have the same sensitivity. And for the view rewrite and the sensitivity calculator, these two modules, and they are the cores of the private SQL, which I will introduce in the next few slides. And in general, the view rewrite module will rewrite some extreme views, say with unbounded sensitivities. And the sensitivity calculator module will compute the sensitivity of each rewrited view. The budget allocator module will assign a fixed privacy budget epsilon to views based on the sensitivity of each view, such that the sum of the sensitivity is smaller than the epsilon. And the private SQL has 4 assignment strategies. The first one is to divide epsilon equally among all the views, and this is the most trivial one. And the second one is to divide epsilon based on the size of the workload for each view. And the third one is to divide epsilon based on the sensitivity of the workload for each view. And the last one is to divide the epsilon proportionally to the sensitivity of each query. The next module, private synopsis generator, will run a differentially private algorithm to generate a synopsis for each view. And PrivateSQL simply makes flexible use of existing algorithms like WNLS and DAWA to achieve this. Now, back into the problem. How to define neighboring multi-relational databases? Before giving its definition, we first define a privacy policy. And the privacy policy is defined as a pair R epsilon, where I is specified as a primary private relation. So it allows the data owner to, with the privacy policy, it allows the data owner to specify which relation should be protected. And the key constraints determine the secondary private relation and hence the cascading definitions. Now, the two multi-relational databases are labeling if one of them is obtained from deleting a minimum set of rows, including one row in the primary private relation. If take the following example, if the person is specified as the primary private relation, then the neighboring databases are differ in only one row, since removing one row in the person only just removed one row in the person. And if the household is the primary private relation, then the person is the secondary private relation due to the foreign key of the household ID HID. And then now the labeling multiple relation databases differ in multiple rows due to the deletion of one row in the household. As mentioned before, the scale of noise depends on the view sensitivity, but it is really hard to estimate view sensitivities since views may involve complex SQL operations like joins. And to address this, the PrivateSQL adapts a rule-based method for estimation. And to address the problem of the sensitivity with large or even unbounded sensitivities, the view rewrite module will introduce the truncation operators to prune outliers. And to keep track of the key constraints, the view rewrite module will also introduce semi-join operators to read-write views. And each view can be viewed is essentially a SQL algebra expression of the base relations, and it can be viewed as a tree, where the leaf nodes are the base relations and the non-leaf nodes are the SQL operators. And the sensitivity is estimated in a bottom-up manner. And according to the rules listed in on the left and the right hand side. For example, the project, select, and the group by operators do not increase the sensitivity, but the group by counter operator doubles it. And the equal join operators equals to the higher one of the sensitivity of the two relations. When the number of rows to be deleted according to the foreign key is larger than a threshold. The view rewrite module will add truncation operators to prune those rows with with unbounded rows, and the view rewrite module will also replace the secondary private relations with semi-joins. To conclude, the private SQL is a differentially private database system which for the first time considers the multiple relations, and some future directions include to let the private SQL to support richer SQL queries, and this leads to improve the view selector module, and to make a tighter sensitivity bound analysis, and this leads to improve the sensitivity calculator module. That's all. Thank you.